Okay, good morning. In today's session, I will be discussing about the temperature stresses that are induced in the metallic bars, structural elements actually. So, the temperature stresses are induced when the free expansion or contraction is restrained. The tendency of any metallic bar is under temperature changes is to undergo deformation. Okay, so if the temperature rises, then the length of the bar will be increased, and if the temperature decreases, then the length of the bar will be decreased. Okay, so at some temperature it will be free of stresses. Okay, it will be free of stresses, and if it is free to expand or contract, then there will be no stresses induced due to change in temperature. If the bar is free to expand or contract, then there will be no stresses induced. No temperature stresses will be induced. When will be the stresses induced due to change in temperature? Only when the bar is restrained from expansion or contraction. Okay. So here, the temperature stresses which are induced in a metallic bar can be determined by equating this change in temperature, change in length due to temperature rise or temperature decrease, okay, to the force which causes that much expansion or contraction. Understand? So here, for example, if the extension is if the extension of the bar due to temperature rise of length L, okay, and the rise of temperature of T is equal to L alpha T. Okay, the change in length is given as L alpha T. Whether it is decrease or increase in length, change in length is given as L alpha T due to change in temperature of T degrees. Okay, so if it is restrained from free expansion or contraction, then the stresses will be developed because the supports are subjected to stresses. The supports which are restraining the expansion or contraction will be subjected to stresses due to change in temperature. For example, let us consider the rise in temperature. Then the bar will tend to expand. For example, if you consider a bar fixed at one end of length L, okay, and material coefficient of expansion, thermal expansion is alpha, and let T be the rise in temperature. Then the increase in length takes place. If it is free to expand, then it expands by delta L, which is given as L alpha T. Okay. At the same time, when this bar is restrained from expanding, restrained from expanding, this delta L will not take place. That means expansion will not take place, which is prevented. Okay, and we know that when the linear expansion, linear displacement is restrained, some force will be developed. Okay, some force will be developed. Compressive force will be developed here. Okay, which causes additional stresses in the member. This force which is developed due to the restraining of the expansion cause some additional stresses in the member, which are called the temperature stresses. Temperature stresses. Okay, understand? So here, if the bar experiences a compressive strain, for example, okay, that means if the extension is prevented, then a compressive stress will be set up in the material, okay, and that is equal to the force required to compress the bar by L alpha T, okay, through a distance L alpha T. Okay, that means the support which is provided here is restraining this expansion, isn't it? So the force required to compress this by delta L, which is given as L alpha T, is the force which is set up in the support, which is developed at the support. Okay, that means if it is free to expand, it expands by delta L, and as the support is preventing it from expansion, it develops a force P. In other words, if it is initially free to expand, it expands by delta L, and let P be the force which causes a compression in the member by of delta L given by L alpha T. Okay, so this force P is the force required to produce a contraction of delta L in the member after being expanded due to temperature. Understand? So the initial length becomes L plus delta L. Now, when the force P is applied to compress by delta L, the initial length becomes L plus delta L, and the decrease in length is delta L. So the compressive strain is delta L by initial length, which is given as L plus delta L or L plus L alpha T, because delta L is L alpha T, the expansion caused by temperature. Okay, and we can write this as delta L is L alpha T divided by L into 1 plus alpha T, and this alpha T when compared to 1 is very very small. Okay, and hence we can neglect that, and we can write the strain as L alpha T by L, which gives the strain as alpha T. Okay, and the stress now is equal to strain into Young's modulus E, capital E. Okay, that is alpha T into E. So knowing the material constant alpha and E, we can find the stresses induced by using this expression L alpha T. Okay, the stress induced in a bar of Young's modulus E and expansion coefficient alpha is equal to alpha T into E. Okay, so that is the stress induced in the material in the bar. Okay, So let us consider one example here. So when a simple bar is restrained from expansion, then a stress of alpha TE is developed, compressive stress. Okay, when the temperature rises, you will have compressive stress, and when temperature decreases, we will have tensile stress. Okay, tensile stress, because it tries to contract, which is prevented. The contraction is prevented. Here the contraction is delta L, and which is prevented, and hence there will be tensile stress developed here. Okay, so consider one simple example. An aluminum alloy bar fixed at its both ends is heated through 20 degree Kelvin. Okay, 20 degree Kelvin. Find the stresses developed in the bar. Take modulus of elasticity and coefficient of linear expansion for the bar material as 80 gigapascals and 20 into 10 power minus 24 into 10 power minus 6 per degree Kelvin. So here rise in temperature, Young's modulus are given, okay, and the coefficient of linear expansion also is given for the material of the bar. So what will be the stress developed? The stress developed is given as alpha TE. Just now we have seen. So by using this, we can find the stress induced in the material of the bar. Okay. So which is 38.4 megapascals. Alpha, T and E, Young's modulus. Okay. So these stresses are developed only when the bar is restrained from free expansion or contraction. Okay. That is one thing. Next, we have seen the case of uniform bar, and let us see the case of tapering bar of circular cross section. Okay, the thermal stresses induced in a circular tapering section. At one end it has diameter d1, at other end it has diameter d2, and d1 is greater than d2 here. Okay, d1 in this case is greater than d2, and it is subjected to an increase in temperature. So the tendency is to expand, which is prevented by the supports. Okay, which is prevented by the supports. The expansion is prevented by the supports provided at ends. So it causes compressive stress. Okay. So yeah, like this L is the length of the bar. D1 is diameter at one end, bigger section, and D2 is the diameter at smaller section end. And T is increase in temperature. Alpha is the coefficient of linear expansion. Okay. So as a result of increase of temperature, the bar will tend to expand. It is a known fact. And as it is fixed, it will cause some compressive stress because it will not allow the free expansion. So it causes some stresses developed in the bar. And what will be the increase in length due to increase in temperature? Delta L is given as L alpha T here. Okay. and let P be the force required to bring the deformed bar to its original length. So if it is free to expand, it expands by L alpha T, okay, which is prevented. That means it is same as applying a force P which causes the deformed bar to uh, retain its original length, okay, which compresses the bar to its original length, okay. And in case of tapering bar, the expansion, the contraction or expansion under the action of force P is given as 4PL by pi e d1 d2, okay, 4PL by pi e d1 d2. So this is the contraction caused by the force P. So now we can equate these two expressions. Okay, this is the expansion caused by temperature, and this is the contraction caused by the force P. Okay, so we equating these two, we get force P required. Okay, force P required, which is pi e d1 d2 alpha t by 4. Here L and L cancels. Okay, so this is the force P which is required to compress a tapering bar by delta L. Here delta L is the expansion caused by the temperature. Okay, as the support is present, it will not allow it to expand, which is similar to applying a force P at one end, which causes a compression of delta L, contraction of delta L. Okay, so delta L is given by this, okay, the contraction due to compressive force P is given by this, and expansion caused by temperature. So these two must be equal. So equating these two, you will get P. Okay. So knowing force P, we can find the maximum stress which will be at the cross section, minimum cross sectional area, at the end where the cross sectional area is minimum, because the stress is given as P by A. Okay. So here P by A2. A2 is the minimum cross sectional area at the end where the diameter is D2. Okay. So how will you get now the stress, maximum stress? P by A2. What is A2? A2 is pi by 4 D2 square. Pi by 4 D2 square. So substituting the value of P here, substituting the value of P in this, we'll get sigma maximum stress as here pi 4 pi cancels, d2 cancels. So it is alpha t e d1 by d2. Alpha t e d1 by d2. This is the maximum stress to which the bar is subjected. Okay, and at the end A, where diameter is d1, the stress is minimum, and which is given as P by A1. P by A1. It is clear. So, and we know that when D1 is equal to D2, the bar will be of uniform diameter. Okay, the bar will be of uniform diameter, and in that case, the stress is given as alpha TE because D1, D2 are equal. So the stress will be same throughout, and that is given as alpha TE. And we have seen that in the previous example. In the bar of uniform cross-sectional area, the temperature stresses are alpha TE. Okay, and in the bar of uniformly tapering section, circular section here, the stress is given as maximum stress alpha TE D1 by D2. Okay, so let us see one example on this also. A circular bar rigidly fixed at its both ends uniformly tapers from 75 millimeters at one end to 50 millimeters at the other end. If its temperature is raised through 26 degree Kelvin, what will be the maximum stress developed in the bar? Take Young's modulus as 200 gigapascals and coefficient of expansion alpha is 12 into 10 power minus 6 per degree Kelvin for the material of the bar. Okay. So, what is given in this? The diameter at one end is 75, the diameter at the other end is 50, and temperature rise 26 degree Kelvin. Okay. So, and Young's modulus and the material constants are also given. So, the maximum stress can be obtained as alpha TE. This is alpha TE into D1 by D2. Just now we have seen the expression. Alpha TE, this is the expression. Alpha TE D1 by D2. We can just substitute the values and find the maximum stress induced in the bar. Okay. Alpha TE D1 by D2. Minimum stress means minimum stress will be this divided by P by A1. P by A1. This is maximum stress, and minimum stress will be P by A1. That means A1 is, this is A2, isn't it? So A1 is pi by 4 D1 square. So P by A gives, what will be the minimum stress now? Alpha TE. Okay, P by A. This divided by A. Here D1 we have to substitute. So D2 will be there. D1 will be, okay. D1 cancels. D2 by D1 you will have. D2 by D1. So alpha TE D2 by D1. This is the minimum stress induced. Okay. Another example. A rigidly fixed circular bar 1.75 meters long uniformly tapers from 125 millimeters diameter at one end to 100 mm diameter at the other. If the maximum stress in the bar is not to exceed 108 megapascals, find the temperature through which it can be heated. Take E and alpha for the bar material as 100 gigapascals and 18 into 10 power minus 6 per degree Kelvin. So the same, similar, but the stress is given, maximum stress, and we are to find the temperature through which it can be heated, maximum temperature. Okay. So sigma maximum is given. So same expression we'll use, alpha TE D1 by D2. because D1, D2 are given, Young's modulus is given, alpha is given. What you need to find? T. Okay. So T will find. Sigma maximum is known, 108. Okay. We have to be careful about units. This is in megapascal, isn't it? Sigma maximum is 108 megapascals, that is Newton per mm square. So you have to substitute the values in the same units on either side. Okay. 100 into 10 cube Newton per mm square, that is E value. Okay. And D1 and D2. So you will get the temperature as 48 degree Kelvin. That means by increasing temperature through 48 degree Kelvin, the maximum stress reaches 108 megapascals. 108 megapascals. Okay. Yeah. So this is about tapering sections. And now let us see the case of bars of varying sections. Some portion of it is of length L and area A1, and the remaining portion is of length L2 and area A2, cross sectional area A2. Okay. So now consider the bar ABC, which is fixed at ends A and C, subjected to an increase in temperature. And if the bar is of uniform section, we know the stress induced is alpha TE. Alpha TE, isn't it? Alpha TE. So here let L1 be the length of portion AB. Sigma 1 is the stress in the portion AB. A1 is cross section area. Similarly, L2, sigma 2 and A2 corresponding values for portion BC. The stresses induced will be different. If the bar is of uniform section, the stress will be same throughout. As the cross sectional area is changing, the stresses also will change. Okay, you will have more stress in portion BC because the area is less. Okay, force will be the same. Compressive force that is developed will be the same. Okay, for equilibrium. So the stress in portion BC will be greater. Sigma 2 will be greater. Okay, than sigma 1 because area A1 is greater than A2. So that is the thing. Alpha is coefficient of expansion for the material of we are assuming here the material is same for both the portions, same material. It can be different also. We will see that case later. Okay. As a result of the increase in temperature, the bar ABC will tend to expand. But since it is fixed at A and C, therefore, it will cause some compressive stress in the body. Moreover, as the thermal stress is shared equally by both the portions, therefore, the condition is sigma 1 A1 is equal to sigma 2 A2. That is equal to the force P. Okay, P is same. So, sigma 1 A1 equal to P and sigma 2 A2 is also equal to P. Understand? The force that is developed at the ends is same for equilibrium, isn't it? So, the portion AC, if you consider the free body diagram of this, it will be subjected to a compressive force P. At the same time, portion BC, it should also be subjected to the same force for equilibrium, isn't it? For equilibrium, the end forces must be same. There is no other force acting and other than temperature rise. So the force developed due to the rise in temperature at the supports must be same. So what does this mean? Here area is A1. The stress developed is sigma. So sigma 1 is equal to P by A1, and here sigma 2 is equal to P by A2. So P is equal to sigma 2 A2 and P equal to here sigma 1 A1. That is P is same in both the cases. So sigma 1 A1 equal to sigma 2 A2. So that is the condition we use here in this case of bars of varying cross sections. Okay. And moreover, the total deformation of the bar, assuming it to be free to expand, is given as, that means if the bar is free to expand without support at one end, the total expansion is given as delta L equal to expansion of portion AB and expansion of portion BC. Sum of the expansions of two portions. Okay. And what will be the expansion of portion AB? Sigma 1 is the stress. So sigma 1 L1 by E is the expansion in portion AB, and sigma 2 L2 by E is the expansion in portion BC. Okay, that is 1 by E into sigma 1 L1 plus sigma 2 L2. This is the case when the material is same for both the portions. Okay, and sometimes if different materials are used, then E1, E2 also will be different. In that case, we cannot take this common here. So sigma 1 L1 by E1 and sigma 2 L2 by E2. The total expansion is given by this expression when materials are different. Materials are different. Okay. Yeah. With this introduction, we can see some examples. Okay. So this is the condition used for solving this type of problems. Okay. So consider this example. A steel rod ABC is firmly held between two rigid supports A and C as shown. Find the stresses developed in the two portions of the rod when it is heated through 15 degree Kelvin. Take Young's modulus as 200 gigapascals and coefficient of expansion 12 into 10 power minus 6 per degree Kelvin. Okay. So you consider the bar. Here the portion A1 is, portion AB is of area 400 mm square and BC is of area 600 mm square. Lengths are 500 mm and 800 mm. Okay. So this is given data. And rise in temperature is given. Material constants alpha and E are given. We'll make a note of these things first. And let now sigma 1 and sigma 2 be the stresses developed in portions AB and BC. And the condition is sigma 1 A1 equal to sigma 2 A2. That we have seen just now. So what is sigma 1 in terms of sigma 2? That we will get here. Because A1, A2 are known. We need to find the stresses sigma 1 and sigma 2. This is one condition that we get. Second condition is obtained by equating this delta L2, delta LS, and if it is free to expand, then delta L1 is L1 alpha T and delta L2 is L2 alpha T. Delta L, the total expansion is sum of these two. Okay, sum of these two. So the total expansion delta L is given by this expansion because the material is same. We have seen this expression just now. We have seen. So the total expansion is given as 1 by E into sigma 1 L1 plus sigma 2 L2. Okay. And sigma 1 in terms of sigma 2. Just now we have obtained the relation. Sigma 1 in terms of sigma 2. Okay. We replace sigma 1 by 1.5 sigma 2 into L1. This is actually L1 is 500. Okay. L1 is 500. Length is 500. Okay. What is length? 500. So this is 500 sigma 2 L2. So this gives sigma 2 and sigma 1 is 1.5 sigma 2. Okay. So if the materials are different, then Young's modulus also will be different and that will be used. That means these terms are taken separately without taking this common. Sigma 1 L1 by E1 plus sigma 2 L2 by E2. So using this, we will find out sigma 2 and then using this relation, we find sigma 1. Okay. That is clear. So when the bars of varying sections are subjected to rise in temperature, change in temperature actually, okay, with the ends fixed, we can find the stresses in these two portions by using these relations. Okay, this is one relation and this is another relation. Okay. Let us take another example. A composite bar made up of aluminum and steel is held between two supports as shown. The bars are stress-free at a temperature of 38 degrees centigrade. What will be the stresses in the two bars when temperature is 21 degrees centigrade? If the supports are unyielding and the supports come nearer to each other by 0.1 millimeter. So the temperature is reduced. So at 38 degrees centigrade, it is stress-free. When the temperature rises above 38, then it will be subjected to expansion and the bar will be under compressive stress. Bar will be subjected to compressive stress because the expansion is prevented. But here, contraction is prevented because the temperature is less than 38. So the bar is subjected to contraction, which is prevented by the supports, and hence the bar will be under tension. Okay. And what is the change in temperature to which it is subjected? 38 minus 21. That is 17 degrees. Change in temperature is 17 degrees. Okay. When the supports are unyielding and when the supports yield by 0.1 millimeter, that means they come closer because it tries to contract. The bar tries to contract, which causes 0.1 mm yielding of supports. Okay. So the material constants are given: 200 gigapascals for steel and 75 gigapascals for aluminum, and coefficient of expansion for steel and aluminum. Okay. So area of steel bar given, it is given, length, area of aluminum bar and its length. So these are given. Temperature change. Here it is decrease, not increase. So it will be subjected to contraction. which causes the supports to come nearer. When it does not cause any yielding of supports, what will be the stress? And when it causes yielding of supports by 0.1 mm, what will be the stresses? First, we will see the case of unyielding supports. Okay, unyielding supports. These are the given constants of materials. So, unyielding supports, first let us consider. The condition is this one. Okay, that is the force is same for both. The sigma s into as is equal to sigma a into a suffix a. That is area of aluminum bar, which is given. Okay, so sigma s in terms of sigma a is 0.5 sigma a. Okay, this is one relation we have. And how about the second relation? If it is free to expand, then the free expansion of the bars is Ls alpha T for steel and La alpha A T is for aluminum bar, which is 0.119 mm. Okay, in both the cases. So the total expansion is 0.238 mm. Okay, so if it is free to expand, then the stress is sigma s into Ls by Es. Delta Ls is given by this, and delta La is given by this. So here sigma s is replaced by 0.5 sigma a. That relation we have just now obtained. Okay, so this gives sigma a. Okay, sigma a is 43.3 megapascals and sigma s is 0.5 times sigma a. That means half of this. Okay, so these are the stresses induced in case of unyielding supports. When the supports yield, then by 0.1 mm. Okay, so the expansion of composite bar will be equal to now 0.138 mm. Okay, because the supports come nearer, the total expansion, if it is free to expand, in case of unyielding supports we have seen it is 0.238. As the supports come closer by 0.1 mm, the expansion is given as 0.238 minus 0.1, that is 0.138. Now that is equated to this sigma s Ls by Es plus sigma a La by E. The remaining is same. Replace sigma s by 0.5 sigma a. Okay, so you will be getting sigma a as 25.1 megapascals and sigma s 12.55 megapascals. Okay, yeah, that's how we solve these problems. Okay, we'll see some more examples and temperature effects on composite bars in the next video. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.